Hello there and welcome to the series on tree, the data structure for interview preparation. So this video is all about getting the fundamentals right. So what we are going to do is we are going to talk about tree data structure on paper. We are going to disregard the coding aspect for now. We'll try to understand what the tree data structure actually is, why do we need it, and uh, we'll try to discover some examples or some applications of the data structure that is being used in modern times. So let's go head first into this data structure. On the whiteboard, I have a tree data structure, and what the circular blank spaces are referred to as nodes, and the one on the top is called root, and the one at the bottom which do not have any branches or connections further are called leaf. And this is called a tree data structure. And why it is called so? Because if you think of a real tree, what happens is we have a root, out of it comes the branches, and then every branch has many branch. So every branch basically uh, divides further into other separate branches, and that is what this tree data structure is like. So on the left over here, what we have is the upside down image of the actual tree that we know. The root is on the top, and then we have the branches going down. So let's talk about some facts about this tree. The tree is basically a graph. So every tree is a graph, but not vice versa is true. Every graph is not a tree. So every tree is a graph, and then if I were to count the number of nodes of this tree, I will say it has 1, 2, 3, 4, 5, 6 nodes, and the interconnection between the nodes is called edges. So we have 1, 2, 3, 4, 5 edges, and that's the speciality of a tree. If it has n nodes, then it must have n minus 1 edges. And if there is a graph which has n nodes and n minus 1 edges, it is a tree. Now the tree that I have drawn is not just any ordinary tree, but it's a very special tree, and there is a term for that tree as well. We call this tree as binary tree. To understand the difference between an ordinary tree and a binary tree, what we need to do is we need to have some counter example for that. So let's say we have a tree like this. So this is also a perfectly well defined tree. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 nodes, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 edges. So it satisfies the tree condition, and therefore it is a tree, it is a graph, it is a tree, and all trees are graph. But it is not a binary tree. The restriction, that the speciality of a binary tree is that every node can have at most just two children. So to understand what is children and what is parent, we need to understand the concept first, the ideology. So for any pair of nodes, what we say is this one is we referred the node top node as a parent, and the branches coming out of that node is termed as children. So these are the children of this parent node. So we have the parent-child relations all across the tree, and over here we have a node which has 3 children, or we have 3 children who have the same parent, and that that breaks the definition of binary tree, because binary tree can have at most just two children. So over here, the root has two children, then each one, this one has two children, and this node has just one child. And then the leaves have no children. So this is a binary tree because there are nodes with 0 children, 1 child, and then 2 children. But there is no node who has more than 2 children. Whereas that is not the case of ordinary tree. It can have as many children as possible, as desired by a node. Now it is important to understand how the data is stored in this structure, because till now it's just some roots or some nodes connected, and the connection is being called edges, but it is a data structure, right? So that how is the data being stored? So what is the data structure that we are most familiar with? I have to admit it is array. What it is a simple linear representation of data 1 2 3 4. So we have four memory locations that have been assigned data 1 2 3 and 4. Very simple to visualize. The way tree represents the same set of data is, how the tree will represent the same set of data is, it will do something like 1 with 2 children, 2 and 3. If I were to draw a binary tree, then it could be 4 here, or I could have given 4 here. It doesn't matter. I could have made it 3 2. The order could have been anything as per our needs and our logics desired for whatever application we are building. But this is how the tree representation will be. So a node is the node contains the data, and also it contains the child, the information that to which child it is connecting, right? So I could store my data something like this. So I have nodes 1 2 3 4 5 and 6, and let's say node 1. So it also stores somehow stores the information. It also stores the information that node 2 and 3 are my children, not 4 5 and 6. And similarly, node 2 stores the information somewhere, somehow, we don't know yet, the information that 4 and 5 are my children. 3 stores the information that 6 is my children, and 6 stores the information that I have no children. And the opposite direction information, the opposite direction flow of opposition information does not take place in tree. That is, 6 doesn't know who is his parent. 6 does not have that information. Similarly, 2 and 3 are not aware that if one is their parent or not. In the data structure, actually, basically we can form the logics to identify who are the parents of whom, but the data structure by itself doesn't store that information explicitly. And that gives me to coin the term unidirected graphs. And you might see that I'm using graphs words a lot of time. It's because of the fact that tree is nothing but a graph, a very restricted case of graph. So unidirected simply means that the nodes can connect in a direction, like we can go from parent to child, but we cannot go from child to parent. That is unidirected. Bidirected could have been, we can go from parent to child and also go from child to parent. Think of it as single lane highway. The unidirected graphs, there are lanes to go from 1 to 2, but you cannot go from 2 to 1 because it is a single lane. Now we understand the tree data structure on paper. We know that the node has to contain the value and also the information of its children, and we will see how to program that in the other video coming up just after this. But for now, we also want to understand what is the need of this data structure. We have arrays. It's quite simple to understand. It's quite uniform. Then why this messy tree structure? I have to admit, like, if this is the tree, a complex one, it's quite a messy structure. Why not store it linearly? It will be space efficient. Tree takes more space. So Why are we doing that? Well, it has its advantages, a lot of advantages, especially in terms of reducing the time for processing the information. And to see the real life examples of tree being used, let's list a couple of them. So, applications. So, talking about applications, the first thing that comes to my mind is HTML DOM. And DOM stands for Document Object Model. Now, if you are familiar with HTML DOM, you must have come across the tree data structure being used for in the official documents or whenever it is being talked about. But if you're not familiar with what HTML DOM is, you can always look up on the internet, or you can better yet search how HTML DOM uses tree. The other thing that comes to my mind when I visualize tree data structure is network routing. So network routing uses the tree data structure as well. To list a couple more, AI, artificial intelligence, ML, machine learning. And precisely in machine learning, I have something that is in my mind is recently I was going across the decision tree. So it is a very efficient algorithm for machine learning, at least on the fundamental stages of machine learning. Then we have the directory or directory on PC. So on PC, if you go on terminal, there is directory, and directory is stored in the form of tree. And in fact, there are some third-party commands or that very beautifully visualize the tree directory in the form of a tree on the terminal itself. But whether you visualize it or not, the truth is that on the back end, the information is there in the form of a tree. So these are some of the examples where tree is used, and you use it in your life. Directory on your PC, you use it. Network routing, the internet, you are using it. HTML websites you are opening are using document or object model. So you are using the benefits of tree data structure without being aware of it. And if so many of examples exist, then the data structure must be very powerful, and it shows the need for the data structure. So next up, we will shift to our editor and actually develop the code for this tree data structure. It's not a difficult one, it's quite a simple one, and I'll walk you through it and walk you through all the logics of it. So we will do that in the next video. So that is it from my side on the tree data structure from the theoretical aspect. Next up is the coding aspect.